All right, hello everyone, and welcome to organic chemistry. So, organic chemistry, I love this stuff. My PhD is in organic chemistry, so it kind of makes sense. But I just think it's really cool because organic chemistry is such a big field, which is weird considering that it's just carbon chemistry, right? And yet it's bigger than all of inorganic chemistry put together. All right, so what is organic chemistry? Well, back in the day, they originally thought that organic chemistry or organic compounds only came from living creatures, right? Until someone went in and synthesized urea, which is an organic compound, it's found in urine, but they synthesized it from a mineral, right? And minerals are not living, and so therefore they had to kind of revamp their definition of organic chemistry. And so the definition that we typically use is that this is carbon chemistry. Okay, it's the study of compounds containing carbon. Now, carbon loves to make four bonds, and it really likes to bond with hydrogen. So you'll notice that in almost every organic compound, you've got a lot of carbon-hydrogen bonds. So just remember that carbon likes to form four bonds, hydrogen likes to form one bond. Okay, now carbon can form double, single, triple bonds, right? As long as they add up to a total of four bonds. We're going to learn what this molecule, what this structure really means. This is capsaicin that's responsible for the hotness of chili peppers, but it contains a lot of carbons and hydrogens. Okay, carbon can also form chains and rings. And these organic compounds may also contain heteroatoms. Hetero means different, so these are atoms that are other than carbon or hydrogen. Okay, so anything beyond carbon and hydrogen is a heteroatom. Now, heteroatoms will typically have some lone pairs on them. Sometimes we explicitly draw them in. You can see the two lone pairs here on oxygen. Sometimes we're lazy and we leave them out when we're drawing a structure. But remember that we need to give everything just enough lone pairs so that it has a total of an octet, right? So for instance, this nitrogen here, it already has one bond, two bonds, three bonds, so it must also have one lone pair, right, in order to have an octet. All right, now if you remember back to our section on geometry, we learned about VSEPR theory, VSEPR, valence shell electron pair repulsion theory, which sounds really scary, but it literally just means that electrons each have negative charges and they repel each other. So in a molecule, these electron pairs will get as far apart from each other as possible. Okay, so what if you had two things bonded to, like this central carbon right here? So we'll call this our central carbon, and it happens to have a hydrogen bonded to it and a carbon bonded to it, right? Two things. So notice that the electrons that are trapped in those bonds get as far apart as possible. They go to opposite sides of the molecule, the opposite sides of that carbon, and we get a bond angle of 180 degrees. We say that this is a linear molecule because it's all in a straight line. Okay. What about if carbon had a double bond? Well, in that case, carbon would be bonded to three different things, right? And those would try to get as far apart from each other as possible. So they'd have bond angles of approximately 120 degrees all the way around. And we call that a trigonal planar geometry because it's in the plane, it's flat, and it's triangular shaped, right? We've got a nice little triangle shape right here. Now, what if we have four things? Well, four gets a little weird because we might look at it and say, oh yeah, I've got a carbon with four things around it, so those look like 90-degree bond angles, right? And that would be true if it were a flat molecule, but remember that these are in three dimensions. And so when you have a central carbon, you've got some hydrogen surrounding it. Because you can work in three dimensions, you can actually put those hydrogens out to the corners of a tetrahedron. So we call this a tetrahedral geometry. And each of those bond angles, they're all identical, and they're all approximately 109.5 degrees. Excuse me. So now remember that these are approximate. It depends on the size of each of those atoms, right? So if I have an oxygen up top and then three hydrogens or something like that, the oxygen would take up some extra space. It would squeeze the others a little bit, but you get the idea. Now, the thing is that when we're trying to draw this, if we draw it like this, that's fine, but it looks two-dimensional, right? It looks flat. And so oftentimes what we'll do is we will draw it in 3 dimensions by using these drawing conventions. So these hydrogens, because they're attached to these nice little solid bonds, just normal lines, those are in the plane of the paper, or in this case, the screen, right? So those are just flat up against the screen. Okay. Now, if it has a solid wedge, like this hydrogen here, that solid wedge means that that hydrogen is pointing out. So imagine that it's kind of pointing towards you, coming out of the screen. And then these little dash marks right here, a dashed wedge, that means that that hydrogen is pointing away from you. So it's kind of like one of those 3D images that you have to cross your eyes or whatever and try to like see it in three dimensions. It's the same type of thing. Okay, we've got 2 hydrogens that are in the plane here, right? That are flat up against it. We've got one that's pointing out towards you and one that's pointing away from you, right? So that would be like these right here. Okay. A tetrahedron, this is a D4 if you're into Dungeons and Dragons. If you're into music, then this is a music stand, right? You've got your little tripod legs right here, kind of pointing down, and you've got your music stand pointing up. Kind of gives you a feel for what it looks like. Now, what if we had something where we've got a lone pair involved? So typically if we have a nitrogen, it'll have a lone pair on it. And so we've got our nitrogen here, and then we've got some other molecules or other atoms kind of pointing away. Then we also have this lone pair up top, right? And so lone pairs do take up space. I mean, they're negatively charged. They're going to repel the other electrons that are in these bonds here, but we can't see them. And so the bond angles will look a lot like a tetrahedral geometry, approximately 109.5. Okay, although it turns out that that lone pair kind of takes up extra space, so it ends up pushing down on the other 3 sides. Imagine a music stand where you kind of squeeze those tripod legs together a little bit. Okay, so it's typically a bit less than 109.5, but close enough. All right, now, what's the molecular geometry on this? Well, this would be called a trigonal pyramidal geometry because we have a pyramid here, and it's a pyramid with a triangular base. Okay, so we call it a trigonal pyramidal geometry. We can't see the electrons, this lone pair right here, and so we don't see that portion of it. So it's kind of like someone popped the top off of a music stand. What about something like a water molecule or an alcohol molecule? So when you have an oxygen, it has 2 lone pairs. So we've got 2 lone pairs over here. And so what ends up happening is we obviously can't see those. And so imagine a tetrahedron or a music stand where you've pulled off like 2 different pieces of that, right? The music stand portion and maybe one of the tripod legs. So all you're left with would be these 2 little legs right here. And so we call this a bent geometry. The bond angles are still about 109.5, a bit less than that again because these lone pairs take up extra space and kind of squeeze those 2 legs together a bit. But this is why we always draw a water molecule as a little Mickey Mouse face, right? It's because the lone pairs, which we can't see, are taking up space over here, right? So these take up space, but we can't see them. All we see is the little Mickey Mouse face, right? Okay, so that's a bent geometry. Now, all of that should hopefully be review, probably from last semester, but at least you kind of have a feel for it. Now, what's some new stuff? Well, one new thing is that organic molecules get big, and so they're a pain to draw. So we can draw out the entire structure like that, but that's a bit of a pain. So instead, we can go ahead and draw a condensed structure. So a condensed structure, all we're doing is we're just kind of saying, okay, look, I've got a carbon attached to 3 hydrogens. I'm going to write that as a CH3. Then I've got a carbon attached to 2 hydrogens, CH2, 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 and on the end, CH3, right? So you can kind of see how those translate to each other. That makes it a little easier to write them out a bit quicker. Okay, what if we have a branch? Because carbon likes to branch things off. So if we have a branch, we just go ahead and say, oh yeah, look at that. Attached to this CH group, I also have this CH3 group that's pointing up. So I just point it up, right? Pretty easy. Now we can condense these even further if we want to. Instead of writing CH3 and then having 3 of these CH2 groups and then another CH3, we can just say we've got a CH3, Then we've got 3 of those CH2 groups in a row, and then another CH3 group. Okay, and we can do the same thing with branches. We could say, look, I've got 2 of these CH3 groups branching off of that CH. There's my CH. I've got 2 of those CH3 groups, followed by a CH2, followed by a CH3, right? Now, you might be tempted to say, well, that seems like a lot of work. Why don't I just say, well, I've got 1, 2, 3, 4, 5 carbons, so that would be C5, and then I've got, let's see, that's 6, 8, 10, 12 hydrogens. So why don't I just write it as C5H12? That condenses it even further, right? Well, you could. The problem is that notice that these 2 molecules would have the exact same formula, right? They'd both be C5H12. And so, we typically try to draw out the structure in some way, even if it's condensed, just to show what the molecule actually looks like so that we can differentiate between different molecules. Okay, so that's kind of some lazy methods for drawing things, but there's an even lazier method that organic chemists have come up with, which is really nice. These are known as skeletal structures, sometimes called bond line structures. I prefer skeletal because it reminds me of Skeletor from He-Man. But anyway, so here's the idea. If I wanted to draw this molecule right here, all I would do is I'd say it contains 1, 2, 3, 4, 5, 6 carbons. So I'm going to draw those in a zigzag line. 1, 2, 3, 4, 5, 6. So notice that the end point of each line represents a carbon, right? And then I've also, so I've got a total of 6 carbons at the end of each one, as well as at the vertex, at the corner of each one, is another carbon. Now, we don't even bother, writing in those dots. We just literally draw that zigzag line, and then that automatically tells me, oh, it's 6 carbons in a line. Now, the other nice thing about this is not only do we not have to draw those carbons out, but we can ignore all the hydrogens. They're what are known as implied hydrogens. Okay, so what that means is that if I were trying to figure out what this structure looks like, I'd say, oh, this carbon right here has 1 bond to something else, so it must also have 3 hydrogens. Because remember that carbon likes to make 4 bonds, right? What about this one? Well, it has 2 bonds already. It must have 2 hydrogens pointing off of it. I could go through and do the same thing for each of these. So after a while of looking at these, your brain automatically just kind of fills in the hydrogens if it needs to. It just says, oh, well, this thing already has 1 bond. It must have 3 hydrogens attached to it. Okay, pretty easy. Now, notice that if you have a heteroatom like an oxygen, a nitrogen, a fluorine, you have to draw those in specifically. And if there are any hydrogens directly attached to those heteroatoms, you also have to draw those in. Okay, so let me go ahead and just practice a little bit. So what does this molecule look like? Well, it's a little pentagon, right? But it's 1, 2, 3, 4, 5 carbons. So I'm going to go ahead and just draw 5 carbons. I'm a little sloppy with it, but that's okay. So 5 carbons, and then I need to draw in my implied hydrogens. So this carbon must have 2 hydrogens. Same thing with each of them, right? Because each of those carbons already had 2 carbon-carbon bonds, but remember that carbon needs a total of 4 bonds. And so that would be my molecule right there. Okay, what about this one? Well, first off, notice that they explicitly drew in the oxygen because it's a heteroatom as well as the hydrogen that's attached to it. They left out all other hydrogens because those are implied. Okay, so I've got a total of 1, 2, 3, 4 carbons in a row. I'm just going to bond those 4 carbons together. Okay, it looks like on carbon number 2, I've got a bond that's going up to an oxygen, which is then bonded to a hydrogen. Okay, now I just need to fill in the blanks, right? So this carbon here has 1 bond already. It's going to need 3 hydrogens. This one only needs 1. This one needs 2. This one needs 3. And then if I want to be very precise, I could also say, you know what, that oxygen only has 2 bonds, right? It needs an octet. So it's going to need 2 lone pairs on it in order to have a full octet of 8 electrons. Okay. All right. Let's try another one. Let's go the other direction this time. So here I've got 1, 2, 3, 4 carbons in a row. So 1, 2, 3, 4 carbons in a row. Okay. Now, it looks like on carbon number 2, I've got one carbon pointing up and one pointing down. So I'm going to point one up and one down. Perfect. So that's my molecule right there. Now, the thing that I should notice, though, well, a couple of things. One, I don't have to draw, oh, I do have to draw something in, because I thought that was a carbon there, but it's not. It's an oxygen, which means that I need to draw in the oxygen as well as any hydrogens that are attached to it. So again, if I want to double check, I should have 1, 2, 3 carbons in a row. 1, 2, 3 carbons in a row. Then one pointing up, one pointing down. That's my molecule right there. So that looks pretty good. Now you might say, well, when you were drawing your initial chain, why did you draw it, starting here and going up? Could I have started up and go down like that? Yeah, you totally could. I could draw this molecule like that. It would be totally fine. Because remember, these are three-dimensional things. So if I rotated it around, those two things would be the exact same molecule. Okay. I could even get a little crazy and draw something like this, where I just point the two carbons kind of pointing off that way. Because again, it's just a slightly different angle, right? It's a different viewpoint. As long as I know that there's this central carbon with these two kind of groups pointing off of it, and then I've got this chain right here, that's fine, right? Okay. Hopefully that's making sense. Let's try one more. So here I've got 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6. Okay. Now, one mistake that people often make is they'll say 1, 2, 3, 4, 5, 6. Do you see what I did there? When I said 1, I went like that. But remember that first line represents 2 carbons. So you always have to, you always have to make sure that you go 1, 2, 3, 4, 5, 6. Okay. An easy way is just check it. Right? I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Right? And then just make sure that you have the one that you actually want. Okay. Okay. So let's go ahead and finish that one up. So we've got 1, 2, 3, 4, 5, 6 carbons. And again, I could have gone this way. 1, 2, 3, 4, 5, 6. That would be fine as well. Okay. And then it looks like on the second carbon here, I've got an OH. I can point it up or down. It doesn't really matter. And then on this carbon, the third one, I've got a carbon, in this case, pointing up. Okay. Now, customarily, it doesn't matter, but customarily, if this thing is kind of pointing up, you typically would put the OH pointing up like that. It just looks a little better. And then this one would point down. Again, they're the exact same thing. It doesn't matter. So don't get bogged down in that. Okay. So let's see. Oh, and just one thing. We could also do the same thing with double or triple bonds. So let's say I had this molecule right here. All right, so there's our molecule. So what I would do is I'd say, okay, I've got 1, 2, 3, 4, 5 carbons in a row. 1, 2, 3, 4, 5. Looks like that first one has a double bond. So let's go ahead and put a double bond there. Looks like the last one on the far right has a triple bond. So let's go ahead and put a triple bond there. And then it looks like carbon number, let's see, 1, 2, 3. Carbon number 3 would be here, has a CH3 group pointing down, just like that. I don't have to draw in any of my hydrogens because they're all implied, right? They're just bonded to carbons. I don't have any heteroatoms, so I don't have to include them, right? Awesome. So the next thing is what I personally think is the most annoying part of organic chemistry, and that's naming, okay? Because it's just a pain, right? It's one of those things where you just have to do it, though. It's like you go to visit another country and you want to learn the language. Part of what you have to do is just learn the grammar, memorize a bunch of vocab words, and then it starts to make sense as you go along later, but you have to put in that initial effort, right? So that's just kind of the way it is with organic chemistry. We have to name things, and unfortunately, back in the day, they didn't have systematic names for things. So someone would discover that, like when an ant or bites you or a bee stings you, they inject an acid, okay, into you, and that's why it burns so much. And so they said, you know what? Because the Latin for ant is formica, we're going to call this formic acid. Okay, and then or they would name it after a person, right? So they'd say, oh, discovered this new compound. My friend's name is Barbara, so I'm going to call this a barbiturate, okay? And literally that's how they came up with those names. So that's fine. I mean, they're easy to remember, right? But they don't tell us anything about the structure. If you say formic acid, unless I happen to know what it is, I don't know what the structure is, right? If you say cocaine, I have no idea what the actual structure of that is, right? I'd have to look it up. Now, on the other hand, there are systematic naming rules that came from the IUPAC, the International Union of Pure and Applied Chemists. A bunch of geeks that get together and they come up with rules. You know those people that just love like rules? Like I'm a board game player, and so I call them rules lawyers, right? Because they're always obsessed about the nitty gritty little things, right? Like, oh, we're playing chess. Oh, black should go first because that's the rule. I don't care. It doesn't matter, right? It's the same thing. I have no idea if that's right anyway. But okay, so but these IUPAC naming rules are useful because that means that every compound will have a unique name, and if you know the name, you automatically know the formula, okay? So here are the rules. First off, we're going to always look for the longest continuous carbon chain, okay? So like, oh, it has 6 carbons in it, and we're going to learn some prefixes on the next slide. So the prefix for 6 is hex, so I'm going to call this hexane, okay? The base name, the A and E ending, tells me that it contains only single bonds. We call these alkanes. So they have only carbon-carbon single bonds. Okay. Next, I have to look for any substituents, any atoms or groups of atoms that are kind of branching off from my chain. Then I'm going to give each of those substituents a name and what's called a locant, a number, kind of an indication of where its location is, right? Is it on carbon number 1 or carbon number 5, right? And then this little rule seems trivial, but it's actually really important, that I always use the lowest numbers possible when giving something a locant, a number. Okay, after I've done that, then I put all of the substituents in alphabetical order. Okay, so let's go ahead and look at these prefixes. And unfortunately, this is just one of those things that you have to memorize, right? Or get it tattooed on your bicep or something, because there's no other way to do it. Okay. Now, luckily, starting at 5, these are just easy Greek prefixes. Like a pentagon has 5 sides, a hexagon has 6 sides, right? Hept means 7. An octopus has 8 arms, right? Non means 9. Dec means 10. Okay, like a decade is 10 years. So those ones are pretty easy. But the first 4, you just kind of have to memorize, right? So meth means 1, eth means 2, prop means 3, but means 4. So for me, I learned it just by counting them off on my fingers. Meth, eth, prop, but. And if you see me like doing this in class, I literally just pull out my fingers and go meth, eth, prop, but. 1, 2, 3, 4, right? And that's how I remember them. Okay, so let's go ahead and try one of these. So if I've got this molecule right here, it contains 1, 2, 3, 4, 5 carbons. So 5 carbons, the prefix is pent. So I write pent. And then I see that they're all single bonds, right, between the carbons. So I'm going to put an A and E ending on the end of it, pentane. Okay. You can also go from the name to the formula, right? So if someone says, oh, this gasoline is high octane, so octane. Oct means 8, right? And then A and E ending tells me that it contains single bonds, right? So octane would look like this. 1, 2, 3, 4, 5, 6, 7, 8. Octane. Easy, right? So that's kind of nice. Now, obviously, we're going to need to practice with the substituent thing, okay? So that's going to take a lot more practice. So let's do a couple of those. So I'm just going to draw a random molecule. And then let's go ahead and put some different substituents on there. Okay, let's do an easy one first. All right, so here, first thing I do is look for my longest chain. 1, 2, 3, 4, 5, 6, 7. 7 carbons. I go back to this. 7 is hept. So I'm going to call this hept. And then I see that it has only single bonds, so heptane. And now I have a substituent this time, right? I've got a fluorine. When you're naming substituents for the halogens, you just put an O ending, like fluorine becomes fluoro, chlorine, chloro, bromine, bromo, so forth, okay? So I'm going to call this fluoroheptane. But I need to specify where it's located, right? Because that fluorine could be anywhere in the molecule. So what I do is I'm going to number 1, 2, 3, 4, 5, 6, 7. Okay. Or I could have numbered from this right-hand side. 1, 2, 3, 4, 5, 6, 7. Notice that if I go with the blue numbering system, the fluorine gets a 2. If I go with the green numbering system, the fluorine gets a 6. Okay. And remember that we always want the lowest numbers possible. Okay. So it's kind of like, imagine that you have to pay for every number you use. I'd rather pay $2 than $6, right? So that means I'm going to go with the blue numbering system and not the red numbering system. So I'm going to go ahead and call this 2-fluoroheptane. Okay, so 2-fluoroheptane would be the name. Okay, so let's try another one. Let's say that I had this molecule. Okay, so in this case, I'm looking for my longest chain. So notice I could number this a couple of ways. I could go 1, 2, 3, 4. It's not a very long chain, right? So I probably don't want to do that. I could go 1, 2, 3, 4, 5, 6, 7. 7 is better than 4, so that's looking a little better. I could have also gone 1, 2, 3, 4, 5, 6. That's not as good. But you can probably already guess the best way would be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Even though it kind of zigzags, it doesn't matter. I'm just looking for the longest chain, okay? Longest chain is 9 carbons. I go back to this chart, nonane, right? Oops, yeah, because non is 9. So I'm going to call this nonane. And then I have a couple of substituents, right? I've got this thing branching off here, this thing branching off here. The rest of it is all part of that chain, okay? Now, when I'm naming a substituent like this, what I would do is, this is a 1-carbon chain, right? Can you see it's just 1 carbon branching off? So I look at this, 1 is meth, right? So I would normally say methane, but the A&E ending tells me that that's like the base chain, right? Instead, I'm going to put a YL ending, so methyl. So that's a methyl group because it's just a 1-carbon branch that's coming off of it. Sure enough, this is also a methyl group over here because it's just 1 carbon that's branching off. If it was 2 carbons branching off, it would be ethyl. If it was 4 carbons branching off, it would be butyl. 7 carbons branching off, heptyl, right? But remember that you always look for the longest chain, which we saw was this thing right here. So that's all included in the base name, nonane. And now I'm just looking for kind of substituents that are coming off of it, right? Okay, so I've got 2 methyl groups. Where are they located? Well, I could go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that would give me a 3 and a 6. Not too bad. Or what if I go with this numbering system? 1, 2, 3, 4, 5, 6, 7. Oh, I somehow double counted. How did I do that? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's better. Okay, I can count. All right. If I did that, that would give me a 4 and a 7. So what do? Well, I just match them up. 3 versus 4, 3 wins. Automatically means I'm going to go with the green numbering system. So I'm going to call this 3, 6. And then I have 2 methyl groups. If they're the same thing, I can just say dimethyl. So I would just call this a 3,6-dimethyl nonane. Okay, meaning that I've got 2 methyl groups. Actually, probably the best way would be look at it this way. Single bonds, 9 carbons in a row, a methyl group, in fact, 2 methyl groups located on carbon 3 and carbon 6. Okay. Now let's try going the other direction. Let's go ahead and I'll give you a name and you figure out the structure. Okay. What if it was a 1-chloro, 4-bromo, octane. Okay, so if I'm going from name to structure, I always like to go in reverse. I would say, okay, octane tells me it's 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go ahead and number these from left to right. I could have gone right to left. It doesn't matter, right? So that's 8 carbons. It looks like I've got a bromo group, a bromine, on carbon number 4. So let's go ahead and put a bromine on carbon 4. I've got a chlorine on carbon 1. That's my molecule, right? I think it's easier to go from the name to the structure than vice versa, but you have to kind of be able to do both. Okay, let's try one more of those. Okay, how about let's say a 3-ethyl 1 iodo pentane. Okay, so in that case, I've got pentane, so it's 5 carbons, 1, 2, 3, 4, 5. Then I'm going to go ahead and number these 1, 2, 3, 4, 5. Okay, and now I've got an iodo group, which is an iodine, on carbon number 1. So carbon number 1 gets an iodine. I've got an ethyl group. Go back to my chart. Ethyl means 2, right? So it's a 2-carbon chunk that's branching off of carbon number 3. So 1, 2. Okay, so that would be my molecule right there. Again, notice that when I have a name, the order of the substituents is determined alphabetically. So ethyl comes before iodo because E comes before I. Okay, I do not put them in order based on the numbers. Okay, so it's always alphabetical. So alphabetize them, give them the numbers, and then put them all in alphabetical order. Okay, all righty. So let's try one more. Let's try a beastly one just to make sure we've got this. Okay, so I'm going to give you some big long molecule. Okay, so I want you to name that thing. You can go ahead and pause the movie for a minute. Otherwise, I'm just going to jump in. Okay, so I'm looking for my longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So that's another nonane. Okay, then I've got substituents. What substituents do I have? Well, bromine is a bromo group. This is a 1-carbon chain, so that is called a methyl group. This is a 2-carbon chain, so that's an ethyl group. Okay, so that's going to tell me what order to put them in, right? Bromo is going to be first, then ethyl, then methyl. But before I can do that, I need to number them. I can either number 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would give me a 3, 4, 9 if I go with that numbering system. Okay, or I could go with 1, 2, 3, 4, 5, 6, 7, 8, 9. That would give me a 1, 6, 7. Okay, so all I do is I just match them up. So the lowest number is 1 versus 3. 1 wins, so therefore I'm going to go with the red numbering system. Okay, so that tells me, let's see, remember I'm going to put them alphabetically, so bromo comes first. So that's going to be a 1 bromo. Then I've got a, let's see, ethyl comes next, right? So ethyl is a 6, so that would be a 6 ethyl. And then methyl comes next alphabetically, so that's going to be a 7 methyl. Now in this case, it just so happens that they're also in order by number, but that's not the rule, right? You always go off of the alphabetical name first. Okay, next thing we need to worry about would be isomers. So isomers are same formula, but different structures, so they're hooked together differently. So you can see in this molecule right here, I've got a formula C4H10. This molecule is also C4H10. Same formula, right? But pretty different structure. This one has the carbons all in a nice chain. This one has them in a chain with a carbon branching off of that second one. Okay, so those are known as isomers. Now, an important thing to realize is that rotation doesn't mean isomerism. So, for instance, with that one that I was drawing, I could draw 4 carbons in a row like that. I could draw 4 carbons in a row like that. I could draw 4 carbons in a row like, let's see, something like that, right? But those are all the exact same molecule, okay? Because it's always 1, 2, 3, 4 carbons in a straight chain. 1, 2, 3, 4 carbons in a straight chain. 1, 2, 3, 4 carbons in a straight chain, okay? Now, if in doubt, if you're, what would an isomer look like? Oh, that would look like an isomer right there, because this has 1, 2, 3 carbons in a straight chain, followed by one that's branching off, okay? When in doubt, just name them. Because if I were naming these, the first 3 of these would all just be 4 carbons. That would just be known as butane. This one, however, 3 carbons, that's known as propane. Then it looks like it has a methyl group on carbon 2, so that would be 2-methyl propane. Has a different name, therefore it is a different compound, right? And it means it must be an isomer. Okay, what else? Well, we can also have stereoisomers. These are weird because they're not only do they have the same formula, they're actually connected in the same order, but oriented differently in space. Okay, a special class of these are known as enantiomers. That's where we have non-superimposable mirror images of each other. Okay, we would say that these are chiral molecules. Okay, what does that mean? Well, think of your hands. Your hands are connected the same way. You've got a palm, 4 fingers and a thumb attached to that palm, right? And yet your 2 hands are not the same, right? If you were to stack them on top of each other, you can't, right? They don't match up. Your thumbs would be pointing different directions. However, if you held it up to a mirror, then your 2 hands are mirror images of each other, right? If you hold your right hand up to the mirror, your reflection is holding up their left hand, okay? And vice versa. So, how do you know if something's chiral? Well, look for 4 different groups on a carbon, okay? So if I have a carbon, maybe with a hydrogen up here, and then let's do a bromine over here, and then let's do an iodine here, and a chlorine over here, okay? So if I were to get a mirror, hold that thing up to a mirror image, it would look like this. Okay, let's see. Okay, so that would be the mirror image of it. And it turns out, believe it or not, those are 2 different molecules. They actually, if you were to build these, get a molecular model kit or just some gumdrops and toothpicks, and build these 2 molecules, you'll find that they really are 2 different things. No matter how you turn them, you can't get them to line up perfectly because they're non-superimposable mirror images. So I would say that these carbons here are chiral, okay, because they have 4 different groups attached to them. And these 2 molecules would be stereoisomers. Specifically, they would be enantiomers of each other. Now you might think, why does it matter? Well, it turns out that the 3-dimensional shape of these molecules is really important. Okay, some examples of this. This first molecule here, this is known as Carvone. There's 2 versions of it, 2 enantiomers, what we call the R and the S version. Okay, if you take organic chemistry, you'll learn all about that. But suffice it to say, there are 2 different enantiomers, and one of them, when those molecules hit your nose, it fits into a receptor in your olfactory senses, and it detects the scent of spearmint. Okay, so one of them smells like spearmint, the other one smells like pumpernickel bread, right? 2 very, very different smells, and yet the molecules are the same. Okay, back in the 60s, there was an anti-nausea drug called thalidomide, and it worked great for things like motion sickness and so forth. And they started giving it to pregnant women because, pregnant women often are morning sick, and so why not help them fight the nausea with this thalidomide drug? The problem is that it comes in two enantiomers, and one of the enantiomers really does work well to get rid of nausea. The other enantiomer is a horrible teratogen. It causes birth defects. And so the women who took this anti-nausea drug ended up having, babies that had no arms or no legs. You can Google thalidomide and see pictures. It's pretty sad. Okay, all simply because of the these two mirror images of each other. Sometimes the mirror images don't really matter, right? So for instance, ibuprofen. One enantiomer of ibuprofen gets rid of headaches. The other enantiomer does absolutely nothing in your body. And so it turns out that the manufacturers found that it's cheaper to just make the pills twice as big and put in, like both enantiomers rather than paying extra to separate out the two enantiomers and only give you the one that's useful. Okay. Another example is if you get a cold and you buy one of those Vicks Vapo inhalers, so it contains this chemical, right? It helps you to breathe and so forth. The mirror image of that is methamphetamine, right? So that means that if you go stand in front of a mirror in your bathroom and hold up your Vicks Vapo inhaler, your mirror image self is actually holding up a container of methamphetamine. So there you go, right? Okay, so it really does matter, especially in biochemistry. All right, the next thing we're going to talk about would be functional groups. Okay, so functional groups, what the heck are these and why do I have some little Star Wars figures? Well, some of you, tragically enough, have probably never seen Star Wars, at least the original trilogy. And yet, even if you've never seen Star Wars before, you probably recognize these two characters, right? You're like, oh, that's Yoda over there on the right, that's Darth Vader on the left, right? And the reason for that is that you kind of recognize certain things like, oh, that guy, he's green and wrinkly and looks like a Muppet. Okay, that's Yoda. It also means that you know certain things about him. He's going to talk funny, he's going to have hair growing out of his ears and so forth. Darth Vader, you recognize his helmet and so forth, and his, all in black style. And so you also know that he's probably likely to breathe funny. He's likely to throw you down an elevator shaft, right? So there are certain things about these characters that you know just by looking at them, right? So that's what functional groups do. These are atoms or groups of atoms that have very specific chemical and physical properties, okay? In other words, if you show me some molecule that I've never seen before in my life, maybe some toxin from some kind of marine snail, right? And you say, oh yeah, this is cone snail venom from this specific tapestry snail. And I've never seen that venom before in my life. I can still probably tell you some specific things about it, like whether it's going to be soluble in water or not, if it's going to have a high or a low melting point and boiling point, things like that, simply because I can recognize the functional groups, these different things that are in there that tell me certain things about the molecule, okay? So you're going to see a bunch of these, and unfortunately, you just kind of have to memorize them, or put them on a chart, right, for a cheat sheet or something. But here's how it's going to look. You're always going to have your functional group listed, and then it's going to be attached to R. R I think of as the rest of the molecule, right? It's just some kind of carbon chain. Doesn't really matter if that's one carbon or whether it's 500 carbons, right? All that we care about is that some kind of carbon chain, okay? So the first class of functional groups, I guess, would be hydrocarbons. So as the name implies, these contain hydrogen and carbon and nothing else, okay? So only carbon and hydrogen. We've already seen alkanes, where we have just carbon-carbon single bonds attaching them together. The ane ending tells us that these are alkanes, right, that they contain single bonds. We can also say that these are saturated hydrocarbons because they are holding as much hydrogen as they possibly can. They also will always have the formula CnH2n plus 2. Okay, it's pretty simple. And that's simply because you've got each carbon is going to have two hydrogens attached, and then you have to have two hydrogens on the end to kind of cap things off. All right. Oh, and you know what? I just realized I totally forgot to tell you about how to name one specific kind of alkane, and those would be cycloalkanes. So a cycloalkane is just like a normal alkane, right? I've got one, two, oops. Let's see, one, what's going on? Change that. Okay. 1, 2, 3, 4, 5, 6 carbons, right? So normally I would call that hexane, but they're in a ring instead of in a straight chain, right? So I would just call that cyclohexane instead. Okay, pretty easy. What if it was something like this? Okay, well, in that case, I've got 4 carbons in a row, so that's going to be let's see, meth, eth, pro, bute. So that's cyclobutane. And then it has a fluoro group attached to it. Now, because I can number these from anywhere I want, it's not like a straight chain where you have to either number from the left-hand side or the right-hand side. I could start here with 1, or I could start here with number 1. I'm going to start here because obviously I want the fluorine to have the lowest number. And then I can either go clockwise or counterclockwise, and in this case it doesn't matter because I don't have any other substituents. So this would be known as fluorocyclobutane. I don't actually have to include the 1 because if I have just one substituent, that substituent is always going to be in the 1 position every time, right? If I have 2 substituents, so let's say it looks something like this, okay, then this would be a well, let's see, let me erase some stuff so I have some extra space. All right, so this would be 5 carbons. So this would be a cyclopentane. And then I have a choice. I can either call this 1 and this 2, like that, which would give me a 1 and a 2. Or I could go 1, 2, and go the other direction, which would give me a 1 and a 2. And unfortunately, when I match these up, the 1 is a tie, the 2 is a tie, and so therefore it's a tie, right? So what do you do if there's a tie? Well, then alphabetical becomes the tiebreaker. So chlorine comes before fluorine first in the alphabet. So let's give chlorine the number 1 position. So this would be 1 chloro, 2 fluoro, cyclopentane. Okay. So remember, if there's a tie all the way down the line, so if this is a tie, even if there's more of them and it's all a tie, only if and only if everything is a tie, then give the first one in alphabetical order, give that the lower number, okay? All right, so anyway, I totally forgot to name those earlier, so now you know how to name cycloalkanes. Okay, now cycloalkanes won't have that same formula because you've linked them together, right? All right, next we've got, you link the 2 ends together. All right, so next we've got alkenes. The ene ending tells me that I've got a double bond in there. So you can see that here between these 2 carbons, I've got a double bond. So we already learned how to name this one. 1, 2, 3, 4, 5, 6 is hexane. What about this one? 1, 2, 3, 4, 5, 6. This would be known as hexene. So the ene ending tells me there's a double bond. And I would actually have to specify that that double bond starts on carbon number 1, right? And then it continues on to carbon number 2. So I call this 1-hexene. Okay, what about if I have a triple bond? 1, 2, 3, 4, 5, 6. So that would be known as hexine. That yne ending tells me there's a triple bond. And specifically, I would have to specify this is 1-hexine because the triple bond is located between carbons 1 and 2. So 1-hexine. Okay. The last kind of molecule is what's known as an aromatic compound. It contains a benzene ring. Benzene is 6 carbons in a ring with alternating double bonds. Okay, and if you remember resonance from way back, I could have drawn that like this. Okay, those are the same. And so even though this looks like a normal alkene with double bonds, it does not behave like an alkene. Because of resonance, it stabilizes it. This benzene molecule is actually really stable. It doesn't react the way an alkene would react. So it's its own class of compounds called aromatic. They were originally called aromatic because the molecules that they found them in happened to have
strong aromas. They were often found in pine sap and things like that. Nowadays, we've found that there are lots of molecules that are aromatic that have no smell, but the name kind of stuck. Okay, so we've already learned about naming alkenes, right? So let's go ahead and just make sure that we know how to do this. So let's say I had a double bond here. Okay, then I would go ahead and say, okay, 1, 2, 3, 4, 5. I could go with this. That would mean the double bond starts on carbon number 2. Or I could go this way, 1, 2, 3, 4, 5, in which case the double bond would start on carbon number 3. I don't like that, right? Because 2 is a lower number, so I would call this 2 and then pentene. Bam, just like that, right? 2-pentene because it's 5 carbons with a double bond. That double bond is located starting on carbon number 2. Turns out the IUPAC people also allow you to name it this way, pent-2-ene, to show that I've got a double bond on carbon 2 in a 5-carbon chain. I personally don't like that just because I think it sounds funny, pent-2-ene. Anyway, but that's just me. Both of them are technically correct. Okay. Now, the thing is, when it comes to double bonds, that if I had a single bond, so let's say that I had this molecule right here. Okay, so because I only have a single bond here, I can freely rotate around that. So that molecule is the exact same thing as this molecule here. Okay, they are completely identical because, again, I only have a single bond here, so there's free rotation around that single bond. I can rotate it any way I want, right? But when I have a double bond, I can't do that because I have what's called a pi bond, right? I have my initial sigma bond, my single bond, and then my pi bond, this double portion of the bond. And if I were to try to twist that around, I would end up breaking that double bond, okay? And so having the 2 chlorines on the bottom, on the same side, I would call these cis, okay? Having the chlorines, one on top, one on bottom, I would call those trans. Okay, they're on opposite sides. And those would be 2 different molecules, okay? So I would have to specify, is it the cis or the trans version of these? Okay, what about alkynes? Alkynes are easy because it's the exact same thing as what we've already been doing. Okay, so if I had that molecule right there, I would go ahead and say, well, 1, 2, 3, 4 carbons, metheth prop-bute, so that would be bute. It'd specifically be butine. And then I'd have to say, well, I'm going to go ahead and number from the right-hand side to give that triple bond the lowest possible number. And so that's going to be 1-butine because the triple bond starts on carbon number 1. And then if I had other substituents, okay, let's say I had a fluorine over here and a chlorine over here, then I would put those at the beginning, right? So this would be a 4-chloro, 3-fluoro. Oh, I'm going to run out of space. Okay, 4-chloro, 3-fluoro, 1-butine. Okay, all right. Now, there is something that's important about both the alkenes and the alkynes, okay? And it seems not very important, but it actually is, okay? Notice that I'm always looking for the longest chain, but it has to contain the double bond. So if I had a molecule like this, okay, so if I had that molecule right there, well, actually, let's make it a little longer, just like that, okay? You might be tempted to say, well, the longest chain is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be a nonane. You'd be wrong because I need the longest chain that contains the double bond. I have to be able to go through the double bond. So it would be 1, 2, 3, 4, 5, 6, 7, 8. So 8 is less than 9, but it doesn't matter because the double bond takes priority. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be a 1-octene. And it looks like it's got a 3-carbon chain coming off of carbon 3. So that's going to be a 3-propyl 1-octene. Okay, so How do you know that the double bond takes priority? Because it changes the ending of the name, and that's an important skill to remember. If a functional group changes the end of the name, if it changes the suffix, then it takes priority. It's more important than anything else in the molecule. Okay, so that also means that when it comes to numbering, if let's say that I had something where it's like, oh, should I give the fluorine the number one position or give the double bond the number one position? The double bond changes the end of the name. The double bond has to get the highest priority. Okay, so it's going to get the lowest number. Same thing goes for alkynes. Okay, I would look at it and I'd say, okay, even if I had a longer chain in the molecule, if that chain didn't go through the triple bond, doesn't matter. I have to go through the triple bond, and I have to give that triple bond the lowest possible number I can. Okay, because it changes the ending. It changes it to an "-ine" instead of an "-ane" or an "-ene." Now you might say, well, what if there's both a double bond and a triple bond? Don't worry, the IUPAC people thought of that too, right? And there are rules for that. We're not going to get into those types of molecules because that's if you take organic chemistry. Okay. Now what about aromatic compounds? So remember, that's where we have a benzene ring, something like that. Okay. So what I would do is I would go ahead and just say, you know what, this is going to be fluorobenzene. Okay, if I had two substituents, then I would go ahead and let's call this one 1, this one 2, 3, 4, 5, 6. I would call that a 1,3-difluorobenzene. All right. Pretty easy, right? Now, unfortunately, there are some common names that are also acceptable as IUPAC names, okay? So one of them is if you happen to have a methyl group attached, like that, this is known as toluene, okay? If I happen to have a benzene ring with an OH attached, that happens to be known as phenol. Okay, just by definition, that's called phenol. Has its own name. Unfortunately, those you just have to memorize. Also, one other thing is, when you draw benzene, remember that you can draw it like this. You can draw it like this, where the double bonds are on the other ones. Or sometimes people will just draw it, because they're feeling lazy, it's just having a circle in the middle, showing that those double bonds are delocalized. They're kind of spread out because of resonance. Okay, we've already learned about these alkyl halides, right? Fluoro, chloro, bromo groups. Okay, notice that those do not change the ending of the name, so they don't get priority, right? I just call it fluoro, 2-fluorohexane or whatever. Okay, alcohols, on the other hand, alcohols, you're always going to have some kind of carbon chain, and then an OH, what's called a hydroxyl group. Hydroxyl group. Okay, if you see a hydroxyl group, it tells you it's an alcohol. Okay, and we're going to learn how to name those. Okay, notice that these are going to change the ending, and so therefore they take priority, right? So if I have this molecule right here, and let's say I have an OH over here, and I have a chlorine over here, you'd say, okay, I can either number 1, 2, 3, 4, 5, 6, or I can number 1, 2, 3, 4, 5, 6. Well, the OH is going to change the ending, so it has to get priority. So this is going to be 6 carbons would be hexane, but because it's an alcohol, I'm going to call that hexanol. I also need to specify it's on carbon number 1, so this is 1-hexanol, and then I put any other substituents on there that I want, right? So this would be a 6-chloro 1-hexanol, just like that, okay? So OL ending for any alcohols. Okay, what other functional groups do we have? We can have an ether. An ether has a carbon chain, single bonded oxygen, then another carbon chain, okay? Turns out ethers do not change the ending of the name, okay? So keep that in mind. So what we've learned, I'll go back at the end and we'll go through, see the ones that change the names. Amines happen to change the ending. Okay, amines have a nitrogen in it. So you've got a nitrogen. That nitrogen could be attached to one R group. It could be attached to two R groups or three R groups. It could have up to 3 carbon chains attached to it. Okay, how do we name them? Well, ethers are easy because we just look for the longest chain, something like this, and then if we have an O, and then let's say something like that, okay? I would say, okay, this is 1, 2, 3, 4, 5, 6, 7. So that would be heptane. And on carbon number, looks like this would be 1, 2, 3. So on carbon number 3, I have an ethyl group attached to an oxygen, right? Ethyl oxygen, I'm going to call that ethoxy. And there's actually no space in between those words. So I'm going to squeeze them together a little more. So 3-ethoxyheptane. So it's kind of nice because they don't change the ending, so they don't get priority. You'd name them just like any other substituent. Okay, amines do change the ending. They're going to, change the ending to amine, which is pretty easy to remember. Okay. Excuse me, apparently I'm allergic to amines. Amines typically smell really bad. The common name of some amines are cadaverine because it smells like cadavers. Putrescine smells like putrefying flesh. Let's see, triethylamine happens to smell like, is the smell of rotting fish. So lots of really bad smelling amines. Alrighty. So let's go ahead and name this molecule right here. So I look for my longest chain that's attached to the amine. 1, 2, 3, 4, 5, 6. Okay, so that would be hexane, but it's attached to a nitrogen, right? So hexanamine. And then I'm going to number this from the side that gives that nitrogen the lowest possible number. Okay, so this would be 2-hexanamine. And then notice that I've got a methyl group. The weird thing about this is the methyl group is not attached to the carbon chain. The methyl group is attached to the nitrogen. I mean, if it was attached over here, I would call that 5-methyl, right? But it's not. It's attached to the amine, so it's attached to the N, so I'm going to call it N-methyl. Okay. So again, if it's attached to a carbon in the chain, just give it a number, right? Like a 5-methyl 2-hexanamine. But if it's attached to the nitrogen, just call it N-methyl. And I could even have something like this. Okay, so looks like I've got 3 different groups attached to that nitrogen. Let's look for the longest one. Looks like this one right here, 1, 2, 3, 4. Although I'm going to number it 1, 2, 3, 4. So this would be a, let's see, methethpropute, so that's bute. That would be butanamine. It would specifically be 1-butanamine. And then it looks like I've got an ethyl group and a propyl group attached to the nitrogen. So that's going to be N-ethyl, N-propyl, 1-butanamine. Okay, so amines are weird, again, just because they could have other carbon chains attached to the nitrogen as well as having carbon chains attached to the carbon chain. All right, the rest of the functional groups we're going to look at always contain the same thing, what's called a carbonyl group. It's a carbon double bonded to an oxygen. Okay, so let's see that. You can see the carbonyl in each of these different functional groups that we're going to be looking at, right? So anyway, we're not going to get to all those quite yet. All right, so what functional groups are they? Well, it depends on where that carbonyl is located and what's attached to it. Okay, if you've got a carbon chain and then you've got your carbonyl, and that carbonyl is kind of at the end of the molecule, so that all you have attached to it is just a hydrogen, like that, kind of at the end. It's called an aldehyde. If, on the other hand, your carbonyl has a carbon chain branching off on this right-hand side and another carbon chain branching off on the left-hand side. So in other words, that carbonyl is in the middle of the chain. Then it's called a ketone. Okay, so two slightly different ones. Either way, they change the ending. Okay, so let's go ahead and look at two of those. Let's say I've got a molecule like this. Okay, so here I've got 4 carbons. 1, 2, 3, 4. So that would be butane. But it's an aldehyde butane, so it's butanal. I know it's an aldehyde because the carbonyl is on the end of the molecule. And because it's an aldehyde, aldehydes are always at the end of the molecule, so I don't have to specify 1 butanal because it's always at position 1. Okay, what if, on the other hand, I had something like this one? Okay, so in this case, here's my carbonyl. That carbonyl is not at the end of the molecule, so it's not an aldehyde, it's actually a ketone. So I would say this is 1, 2, 3, 4, 5, 6. So that would be hexane. Technically, it would be hexanone, okay, because it's a ketone. And it would be 3-hexanone. And I do have to specify because that ketone could have been located here, it could have been here, it could have been here, right? There's multiple locations for that ketone to be. I have to specify where it's at in the molecule, okay? So aldehydes, ketones. Okay, carboxylic acids. So carboxylic acid, I've got my carbonyl group, but notice that that carbonyl group is attached to a hydroxyl group, an OH group. So it almost looks like an aldehyde mixed with a ketone, right? But it turns out that when they're combined like that, we call it a carboxylic acid. On the other hand, if I have a carbonyl, then an oxygen, then another carbon chain, then it's called an ester. It's kind of like a mix between a ketone and a ketone or an aldehyde and what's it called? An ether group, right? But it's its own specific thing. We call it an ester. Okay. So turns out that both of those change the ending as well. Okay. If it's a carboxylic acid, changes it to oic acid. So let's say that I had this molecule right here. So that would be carbon 1, 2, 3, 4, 5. That would be pentane, but it's a carboxylic acid, so pentanoic acid. And carboxylic acids, that group is always on the end, right? It has to be on the end, just like an aldehyde. Okay, esters are a little more complicated. Okay, so let's say I have this molecule right here. Okay, first thing you need to do is look for your carbonyl. Here's my carbonyl, so therefore that's carbon number 1. Okay, that also means that that's the base chain, even though it's this chain over here is 1, 2, 3, 4, 5 carbons long, right? But because my carbonyl is here, that's my base chain. So I'm going to call that butanoate. So it has an O8 ending. So that's butanoate. And then it also has something attached to it. It looks like this would be a 1-pentyl butanoate, because attached to that oxygen here is a 5-carbon chain, so that's pentyl, and it's attached on carbon number 1 of that. So 1-pentyl butanoate. Okay. Esters tend to smell really, really good. Okay, a lot of the fruit smells, raspberry, pineapple, banana, all come from esters. Wintergreen is an ester, the smell of wintergreen. Rum, a lot of different things have esters in them that give them good smells. Okay, almost there, right? I think, yep, just one more functional group. So these would be our amides. Amides look like amines because they have a nitrogen in there, but it's a nitrogen that's attached to a carbonyl. Now remember, with nitrogen, you could have other carbon chains attached to that nitrogen, right? So, or you might not. All right, so these do change the ending to amide. So let's go ahead and see what that would look like. So if I had this molecule here, I would look for my carbonyl, right? That chain contains 1, 2, 3, 4 carbons. So that would be butane, but it has an amide, so it's butanamide. And then it looks like I've got a methyl group attached to that nitrogen, so this one would be specifically N-methyl butanamide. I should have actually put those words together, N-methyl butanamide. Okay, go through the textbook. You know, you can do a bunch of these practice ones. It takes a while to learn them. It's kind of a pain. Okay, so I'm going to go back for a second, and I'm going to specifically look at things that change the ending. Okay, alkenes change the ending to ENE, so they take priority. Alkynes change the ending to YNE, so they take priority. Alcohols change the ending to OL, so they take priority. Ethers do not change the ending, so they don't take priority. Amines do, because they change the ending. And then everything else does as well. Okay, aldehydes and ketones change it to al or one. Carboxylic acids change it to oic acid. Esters change it to OH. Amides change it to amide, right? So all of those take priority. Again, what if you had multiple functional groups in the same molecule? So which would take priority, an alcohol or an amine? Again, there are rules for that. It turns out the alcohol would take priority, but you do not need to worry about those because I won't give you something where you have to name a molecule with multiple functional groups. I might give you a molecule like this and say, what are all the different functional groups in there? That would be fair game, but I wouldn't ask you to name it. Okay, so let's practice that. Oh, it looks like I have an amine over here, right? Because it's a nitrogen that's not attached to a carbonyl. Here's another amine. Okay, this thing right here, that benzene ring, that's called an aromatic group. Here I have a carbonyl, but it's also attached to an oxygen, which is further attached to a carbon chain. So that is an ester. Okay, so you may have to practice with a bunch of those just to make sure that you can see all of those different functional groups. Okay, whew, that's a lot of stuff, right? So that really is a bit of a pain. So let's take a quick break and so let's see, I'm just gonna switch over real quick to my camera. Okay, let's switch that around. Okay, hey there. All right, awesome. So when we're looking at naming these different functional groups, remember that certain ones take priority, right? So it's kind of like if you have one of these cash cards. I should block out the number so it doesn't matter. Okay, anyway, but you notice that a lot of times nowadays they're putting these little chips on it, right? And so because that's really the most important thing, you can actually just hold this up to the little scanner and it'll mark it, right? And so wherever the chip is, that's the most important thing. So in this case, the chip is on in my case, my left-hand side, right over here, okay? But what if, on the other hand, what if I just went ahead and shook it, right? I could just shake that whole thing up and I could have the chip over here on this side now, right? And so obviously, again, that's the most important portion of the card, and it's over here this time. So that's the most important thing, okay? Totally makes sense, right? Okay, awesome. Okay, so let's go back over here. Let's go ahead and do some easy stuff for a little bit. That sounds kind of nice, right? I told you that naming is the most annoying part of the whole thing. It's just the way it is, though. All right, so what are some kind of simple things that we could know about these? Well, we know certain properties about these because if I have something that's just a bunch of carbons and hydrogens, it's only going to exhibit London dispersion forces. Remember from our chapter on intermolecular attractive forces, there's London dispersion, that's the weakest. Then you've got dipole-dipole, which is a bit stronger. Then you've got hydrogen bonding, which is the strongest. So oftentimes, they'll only have really weak forces, so they typically have very low boiling points, low melting points, which means that they're typically liquids or gases at room temperature. Okay, so something like methane is natural gas, right? It's a gas at room temperature. Something like propane, right, or butane, liquids at room temperature, right, or gases, I guess, actually. or very volatile liquids. All right. Now the other thing is that remember that because we have just a whole bunch of carbons and hydrogens in our molecule, carbon and hydrogen are completely nonpolar, right? They have very similar electronegativity, so therefore most organic molecules are nonpolar. The only exception is if they have heteroatoms. If I suddenly had a bunch of nitrogens or hydrogens in there, or fluorines in there, those things would make them more polar, right? Because now you've got heteroatoms. But if it's just carbons and hydrogens, nonpolar. Now remember that water is very polar, and so like dissolves like, so most organic molecules are not soluble in water. Okay, so if I had something like hexane, 1, 2, 3, 4, 5, 6, that would not dissolve in water at all. Okay, if I have small organic molecules like ethanol, in that case, this hydroxyl group makes it more polar, which means that that probably would, actually does dissolve very nicely in water. Okay, so you can actually predict whether something's going to be soluble in water just by looking at the formula, right? Looking for heteroatoms. So in this case, a whole bunch of carbons and hydrogens, that's nonpolar. That would not dissolve in water. Here, short molecule, very short carbon chain with a heteroatom, that oxygen. So yeah, that would be very soluble in water. Okay, what about something like this molecule where you've got a whole bunch of carbons and hydrogens and then one measly little OH over here? So the OH is trying to make it soluble in water, it's trying to make it polar, but this carbon chain is just too big, right? So that's non-polar. It would not be soluble in water. That's actually cholesterol, which is why, if you eat too many French fries like I do, your cholesterol levels go up. And that means that the cholesterol will actually precipitate out of the water in your bloodstream, and it forms plaque on the inside of your arteries, and that's bad, right? Gives you a heart attack. Okay. A simple rule of thumb is every oxygen can pull about 3 carbons into water. So if I had a carbon chain that contained 3 carbons and then an OH, yeah, that would be pretty soluble in water. But if I had a whole bunch of carbons like this with one little OH on it, no. That's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's no way that would be soluble in water. Okay. It would be quite soluble in other nonpolar things, like it would be soluble in hexane, right? Because hexane is nonpolar and like dissolves like. Okay, what about vitamins? Well, this gets into a bit of biochemistry, but vitamins are just organic compounds that your body needs small amounts of in order to help your enzymes function properly. Your body can't synthesize them on their own typically, so you have to get them in your diet. Some are water soluble, some are fat soluble. You can tell just by looking at them, right? So in this case, big old carbon chain, a measly little OH, so vitamin A would not be soluble in water, okay? What about vitamin C? Oh yeah, look at this. I've got like so many oxygens in there. So that's going to make this very soluble in water. Okay, which is why it's pretty much impossible to overdose on vitamin C. If you take a mega dose of vitamin C, your body takes what it needs and then it excretes the rest in your urine. And you have expensive urine and that's it, right? On the other hand, if I have something like vitamin A or vitamin D, if I took a whole bottle full of those, I could overdose on it because these are fat soluble. They don't dissolve in water. Your body cannot excrete it through your urine, and so it builds up in your liver and fatty tissue, and you can get to too high levels and overdose on it. Okay, we're almost done, but we're actually at the most exciting portion, at least I think, which is the reactions that these organic molecules can undergo. Okay, so we've learned naming, we've learned some kind of properties of them, but what about the reactions that they can do? Well, the first reaction that organic molecules can undergo would be combustion, which is literally you just take the molecule, you mix it with some oxygen, you light a spark, and you burn it. When you do combustion of organic molecules, you always get out carbon dioxide and water. Okay, that's it. Okay, substitution. Substitution occurs when I swap one thing in for something else. So notice that I had 4 hydrogens attached to that carbon. I'm going to swap one of those hydrogens out and replace it with a chlorine. That spare hydrogen went over here and attached to the spare chlorine, and they went on their way. Okay, so that's a substitution reaction, swapping one atom for another. Okay, the next type of reaction would be addition. This is where you're adding something to it, and these work really well with when you have a double or a triple bond, so an alkene or an alkyne. So for instance, if I had this molecule right here, I could add in some hydrogen. It typically requires a catalyst, so that catalyst would often be nickel, it could be palladium, it could be platinum. So you'll typically see one of those things above or below the reaction arrow, just saying that you need that in order for the reaction to take place at a decent speed. Okay. When you do that, what I'm actually going to do is I'm going to put these hydrogens in red. Okay. Just so that you can see that what's going to happen is I had that double bond there, right? I'm going to break that double bond, and I'm going to add a hydrogen to each of those. Okay, it's called hydrogenation. You're hydrogenating it, right? You're adding hydrogen, one to each of those two things. It could happen with a triple bond as well. So if I had that right there, okay, I could add in, actually, I could add in two hydrogens. So I'll add in a red one and a green one. So what's going to happen here is I'm going to go ahead and break one of those bonds, add in a hydrogen. It's kind of going off the page, but add in two hydrogens there, one to each. Then I could come in and break the other bond, and I could add in a hydrogen to each of those, right? So addition reactions need a pi bond. You need a double or a triple bond, and all you do is you go in and you break those double or triple bonds and you add in hydrogen. Okay. We could do the same thing with halogenation. This is just where we're adding a halogen. Halogens are typically abbreviated X, right? So I could add in Br2. And again, all I do is I break that double bond right there and add in a bromine to each side. Or it could have been a chlorine to each side, or an iodine or fluorine to each side, right? Halogenation. It could be any halogen. Hydrohalogenation occurs when I add something like HBr. So notice that this time, when I break that pi bond, I'm going to add in an H to one side and a Br to the other. Okay, I'm going to add an H and a Br. Okay, so just like before, I added an H to both sides, I added a Br to each side, or I added an H and a Br to each side, right? So those are addition reactions. Now, one important thing is, notice that when we were doing this, I had my pi bond there, right? And I'm adding in HBr. So when I do that, I could end up with two different products. I could have added in the H here and the Br here, or I could have added the Br here and the H here, and I would get two different isomers, right? They would be two different molecules. It turns out that this is what we're going to get. You might say, how do you know, right? It's because of a tricky little rule called Markovnikov's rule. And I don't even know if I'm spelling that right, but Markovnikov's rule. Okay, Russian chemist who figured this out, right? And it turns out that what's happening here is, have you ever heard that that saying, the rich get rich and the poor get poorer, like the rich get richer, the poor get poorer, right? So that's what's happening here. If I were to draw in my implied hydrogens, you would see that the carbon on the left is already attached to two hydrogens. The carbon on the right is only attached to one hydrogen. So the carbon on the left is richer in hydrogen. It has two, so it gets another one. So sure enough, you add the hydrogen there. The other carbon gets the bromine, right? Okay, so let's try another one. Okay, what about this molecule? Let's say I was adding in HCl this time. So what would my product be? Well, what I would do is I would just go ahead and draw this in. Okay, so let's draw in our implied hydrogens. So this carbon doesn't have any hydrogens on it, right? Because it already has 4 bonds. This one, however, does have a hydrogen. So who's richer in hydrogen? carbon on the left, right? So sure enough, when we break this pi bond right here, break that double bond, we're going to go ahead and add in a hydrogen here. This one gets stuck with the chlorine, okay? And that would be your major product. You might get a little bit of the reversed one, but not much at all. Okay, so Markovnikov's rule allows you to figure out who gets the hydrogen when you're doing a hydrohalogenation. Okay, now what about if I had something like an alcohol? Well, alcohols, they can do a couple of different types of reactions. They can do a substitution reaction. So notice that I've got an OH attached to my carbon. I'm going to go ahead and I'm going to swap out that OH for a Cl, for a chlorine. Okay, the OH partnered up with the H plus OH makes H2O, water, right? So that's what happened to those. Okay, so that's a substitution, swapping out one for another. And you'll go into a lot of different types of substitution reactions if you go on and take organic chemistry. Okay, now what about elimination? Elimination is the exact opposite of an addition reaction, right? So it turns out, oh, I actually forgot one of these that I should have mentioned. So let me actually go into that real quick. One of the things that I could add in is I could actually add in water. When I add in water, it's like an HOH, right? H2O is HOH. So again, who's going to get the hydrogen? And who gets the OH? Okay. Well, it looks like hydrogen on the left has more hydrogens, right? So it's going to get this H right here, which means that the OH is going to get attached over here, okay? So notice that I can take a double bond, I can add water to it, and add an H and an OH. Elimination is just the opposite. I take something that had an OH attached to it. Okay, well actually let's put the OH over here for fun. And what I'm going to do is I'm going to go ahead and remove an H from a next door neighbor. So I'm going to pull out an OH and an H to make water. And in the process, I'm going to make an alkene. Looks like that. Okay. Now, you might say, well, what if I had this one right here? Okay. So notice that when I heat this thing up, I could either form the alkene like this, or I could form the alkene like this, right? Because what I can do is I can pull off an H from over here, or I can pull an H off from over here, right? Because I'm going to need an OH. I'm going to remove an OH, and I'm going to remove an H. But who loses the H? Okay. Well, luckily, there's a Russian rule for this as well. It's called Zaitsev's rule. Okay. Now, in the that saying, I said the rich get richer. The other half of that is the poor get poorer, right? So if you're going to remove a hydrogen, always remove it from the one that's poorest in hydrogen already. So this thing has 3 hydrogens. This carbon only has 2 hydrogens. So too bad, the poor get poorer. We're going to go ahead and remove one of these hydrogens right here. So we're going to remove that. So that means we're going to get this molecule right here. Because when we remove the OH and the H, the double bond has to be formed between them. Okay, so the rich get richer. So when you add in a hydrogen, add it to the one that has the most hydrogen. The poor get poorer. When you remove a hydrogen, remove it from the one that has the fewest hydrogens. In organic chemistry, they go through carefully and they explain why all of this happens, which is really important. But for this class, you just need to know what happens. And so the rich get richer, poor get poorer. That's an easy way to remember it. Okay. Oh, the next type of reaction that we can have would be oxidation. Okay. So oxidation, if you remember in a previous chapter, we talked about oil rig, where oxidation is loss of electrons and reduction is gain of electrons. Well, that's one way to think of it. In organic chemistry, though, an easy way to remember it is that oxidation means gaining carbon-oxygen bonds. reduction means reducing the number of carbon-oxygen bonds. Okay, so let's go ahead and see what that looks like. So let's say I have this primary alcohol right here. It's called a primary alcohol because the carbon that the OH is attached to is only bonded to one other carbon chain. So I've got a primary alcohol. I can oxidize it. That's what this little brackets with an O means, just means oxidation. And there's a bunch of different chemicals that you could use to oxidize it. But when I do that, I went from having one carbon-oxygen bond to having two carbon-oxygen bonds, right? So that's an oxidation. I could actually oxidize that thing again, and instead of having two, now I have three carbon-oxygen bonds. Okay. Now, what if I did the same thing with a secondary alcohol? Okay, so this carbon is bonded to two other carbons, so it's a secondary alcohol. It currently has one carbon-oxygen bond. Now I have two, right? So that's an oxidation. Could I oxidize it further? Well, if I tried, I would have to add another OH like that, and that would give this carbon 5 bonds. That's not possible, so that's not allowed. I can't give carbon more than 5 bonds, or more than 4 bonds. So this would just be no reaction. What if I tried this with a tertiary alcohol? Tertiary alcohol, that carbon is bonded to 3 other carbons. So when I oxidize it, I would have to make something like this. Could I do that? No, because that carbon would have 1, 2, 3, 4, 5 bonds. That's not allowed. So again, I would say no reaction. Okay. So what that means is that primary alcohols can be oxidized into, that's an aldehyde, right? And then aldehydes can be further oxidized into carboxylic acids. A secondary alcohol can be oxidized into a ketone, but a ketone can't be oxidized any further. And a tertiary alcohol can't be oxidized at all. Okay? So that's an oxidation reaction. And then the last type of reaction would be a condensation reaction. Okay, this is where you take an acid, something like this molecule right here. You mix it with an alcohol. You typically add an acid catalyst. You'll often see it written as H plus or H3O plus, just some kind of acid. And then we end up making an ester. Remember, an ester has a carbonyl, then an oxygen, then this right here. All we're doing is we're simply removing an OH from here and an H from here. Notice that in the process, we end up making a water molecule, which we don't really care about, right? But we also end up making an ester. We end up bonding between this carbonyl and this carbon right here. So we got this carbonyl. Actually, I shouldn't say that. Carbon goes from this carbonyl to this oxygen, which is then bonded to the rest of it, right? So this carbonyl to this oxygen, which is then bonded to the rest of it. This is actually a really fun lab to do because you take a carboxylic acid, which typically smells really bad. Butyric acid, for instance, this one right here smells like BO, right? Like body odor, or like rancid butter. And then you mix it with an alcohol, you put in a drop of like sulfuric acid, and you end up getting an ester, and esters smell really good. So when you do this lab, face to face, the lab starts smelling like starts out smelling like a locker room, right? A whole bunch of body odor. And then as the reaction takes place, suddenly you start smelling bananas and, cherries and, peaches and pineapple, and it suddenly smells really, really good. So it's kind of a fun lab. Anyway, so that's a happy little place to end. I know that was a big chapter. There's a lot going on there, right? So just keep that in mind. There is a lot going on. This is just an overview of organic chemistry. People spend their entire careers learning organic chemistry, right? At the minimum, you got to do a full year of it just to even get the basics of it. So trying to do it in just like an hour or two lecture is pretty tough. But hopefully at least gave you enough information that you feel like you have a bit of background on it and can do the homework. All right. So thanks for sticking around all the way to the end. I'll see you next time.